The theory video for the Ferrocene experiment, and what this does is kind of explains how column chromatography works, so how you're actually separating these two compounds. Now, column chromatography is a really important technique that we use to separate and purify molecules, and that's because quite often when we do an experiment, there isn't a big difference between the properties of the molecules that we use, like our starter materials and our products, for example. So it's difficult to separate them and purify them using techniques like recrystallization or distillation. So, but with column chromatography, we can separate molecules based on their polarity, where there is a small change. And here you can see most of ferrocene and acetyl ferrocene has a similar structure, but this carbonyl compound that we have here just means that acetyl ferrocene has a slightly more polar compound than ferrocene, and so column chromatography is a way that can kind of expose that difference that allows us to purify the two molecules and separate them from one another. In this theory video, I'm going to explain how it works. Okay, so I think I've explained kind of this first point. It's because we can't always separate molecules based on other types of properties, like how well they dissolve in solvents for like a recrystallization, or their boiling points based on like for distillation, for example. But if they've got different polarities, then we can separate them with column chromatography. So something you should be familiar with already is that we can separate molecules on polarity using chromatography with silica. We've seen this with thin layer chromatography, where if we've got a TLC plate with that white powder called silica on there, then polar molecules are more strongly attracted to the silica, okay, through intermolecular forces like hydrogen bonding, okay, whereas less polar molecules are less attracted to the silica. So if we pass a solvent through, so the solvent runs up a TLC plate, okay, then what happens is the less polar molecules, less attracted to the silica, they run up higher, like this ketone here, whereas a more polar molecule will stick and be attracted to the silica and will run more slowly up the TLC plates. Okay, this is exactly the same principle behind what happens with column chromatography. Okay, compounds that are more polar will stick to the silica column, and they will run and travel more slowly down a column, whereas compounds which are less polar will run more quickly down a column. Okay, so it's just like TLC, except instead of the solvent running up a TLC plate, we have the solvent at the top of the column, and we run them down the column. Okay, so what we do is we load a sample, we make a column of silica gel with solvent in there. Then we add our sample as a thin sort of band, our mixture, and then we add solvent on the top, and we call the silica the stationary phase. We call the solvent that we're passing through the mobile phase. Okay, and what happens then is the less polar molecules, the ones that don't stick to silica as strongly, they pass through the column much more quickly. Okay, and we can see that sort of green band here with the weaker interactions passing through, coming out through the bottom of the column. They reach the bottom of the column more sooner than polar molecules, which have stronger interactions with the column. So you can see that second band comes off later down the column. What we do at the end of the column is we collect the solvent that comes off the bottom of the column in fractions, so either conical flasks or in test tubes. And so what happens is the compounds that elute first down the column with the weaker interactions, eventually they will be collected in test tubes or a conical flask. Okay, so they become eluted down at the bottom, whilst the more polar molecule stays on the column. Okay, so then we can, and then what we do is once we've collected our sort of first molecule, the one with the weaker interactions, we can then change the test tube or the conical flask that's collecting the fractions at the bottom of the column. Our second, more polar molecule can then reach the bottom of the column later and be collected into a separate conical flask or test tube. And with these two molecules eluting differently and being collected in separate flasks, then we've basically been able to separate them through the column and partition them and basically purify them as well. Okay, that's how columns sort of work. With the ferrocene column, essentially, ferrocene is the compound that it has a weaker interactions. It comes off first down the bottom of the column, and then acetylferrocene is the second molecule that gets eluted, collected in a separate conical flask, and that's how we purify the two molecules. With the ferrocene experiment, both compounds are coloured, so you can see the two bands being separated and being collected, and you know when you've sort of collected your ferrocene into the first conical flask, you then see that yellow band go into the conical flask. When that's finished, you know when to sort of swap conical flasks and have that sort of second sort of red-orange band collect into the second conical flask. But quite often, especially with organic molecules, they don't have any coloration. You cannot see when they've come off the column. So what we do is we use thin layer chromatography to kind of work out what we've got in each of our fractions. Okay, so here's an example of a TLC. So let's imagine that before we run our column, we had a mixture of three compounds, and we can see three spots there. Okay, they're separated by their polarity. The least polar spot is some impurity that's formed in the reaction. The product of the reaction is like the middle spot, so it's middling polarity. And the most polar compound we have is our starter material. So imagine we have a mixture of the three. We run a column to try and purify the mixture. We're obviously trying to collect the product and isolate it from the impurity and the starter material. We would collect what comes off the bottom of the column in test tube fractions, and then we'd run the TLC fractions. Okay, and as we can see in our TLC, the least polar compounds come off first, so the impurity comes off first. Then in the second test tube fraction, what happens here in this example is sometimes, you get, maybe the impurity hasn't run off and eluted off the column before the product starts collecting in the test tube. So we have a mixed fraction here in our second test tube fraction. Okay, then we start collecting test tube fractions which just has the product in there, but then again, before our product has eluted nicely, before our starter material starts to elute in some of the fractions as well before it elutes off in the end. Okay, this example is to kind of show you that with column chromatography you don't always get perfect separation. Sometimes you have to tweak how you run a column to get things to separate nicely. So it's important to analyze columns by TLC if they're sort of molecules you can't see, but also if you get something like this where we don't get perfect separation, then what we would do is we would analyze the fractions by TLC, which will find out which ones are pure, and collect them by collect the test tubes that only have pure fractions. So in this case, this example, test tubes 3, 4 and 5, collect them together, then remove the solvent, sort of remove them on a rotary evaporator, and you're left with pure compound. And then you can either collect the other fractions that have mixed fractions in there if you need them, if you still need to get that product that's sort of contaminated with the impurity or the starter material, then you could perhaps have a repeat, run the column again, have another go and see if you can get some pure material there as well. Okay, so what are the factors that affect how well things separate on a column. So the polarity of the solvent system is important. So it's a ratio of ethyl acetate and petroleum ether. Okay, so you usually have to get the balance right, so that if you're if you have if your solution is too polar, so maybe the ratio of ethyl acetate is too high, then what can happen is all your compounds sort of run quite quickly down the column, and they don't really separate. Okay, so what you need to do is make sure you have the right, but if you have too much petroleum ether and it's really too non-polar, then the column just takes too long to run. Everything just sort of stays at the top of the column and just runs really, really slowly, and you're not collecting anything or having anything coming out the bottom of the column coming off for quite a long time. So usually what we do is we have a ratio that allows things like, impurities or products, things to separate quite nicely and run and separate like they have done here, so we can collect them into different test tube or conical flask fractions. Other thing that affects the size of the column is how much silica we have, the size of the column that we use. Again, if we only have a short column, then sometimes what can happen is we don't give enough silica, we don't give the compounds enough chance to separate on the silica, so then they all become eluted together. Again, if we use too much silica, then it just takes too long for the compounds to run down the column and be collected out at the end in the fractions. So we usually try and get a balance right of making sure we have the right amount of silica that allows the compounds to separate, but also be eluted in good time as well. And the final thing is actually how much solvent we collect in the test tube fractions. So again, if we have large test tube or conical flask, large conical flask where we're collecting lots of solvent, then what can happen is we sort of collect the first compound, but then we're collecting the second compound that's been eluted before we swap over to a new test tube or conical flask. And again, on the flip side, if we only collect tiny amounts, then we're just using, we can end up using lots and lots of test tubes where nothing is coming out either. So again, it's about getting the right balance so that we're sort of collecting the right volume where we're sort of collecting the materials that we want in separate test tube fractions, but also it's sort of being collected in a reasonable number of fractions and test tubes as well. Okay, so that's the theory behind sort of column chromatography and how it works.